My name is Aakash Nukala, and today I will be presenting on Alzheimer's disease and the potential CRISPR-Cas9 the treatment strategy. I will begin by explaining what Alzheimer's is at a basic level, then move into a deeper look at how it develops, its prevalence, and why addressing it is such an urgent challenge. Finally, I will connect this foundation to how CRISPR-Cas9 can target the root causes of the disease rather than just the symptoms. This is the agenda for today. I want to introduce Alzheimer's disease and then introduce CRISPR-Cas9 and the role of CRISPR-Cas9 in curing Alzheimer's and the challenges of this curing treatment method. What is Alzheimer's? Alzheimer's disease is a progressive neurodegenerative disorder and the leading cause of dementia worldwide. It gradually impairs memory, reasoning, and the ability to perform daily activities, ultimately leading to a complete loss of independence. Unlike normal aging, Alzheimer's is marked by distinct pathological changes in the brain, which progressively damage and kill neurons. Current treatments often for temporary relief or symptoms, but do not halt or reverse the disease itself. A deeper look at Alzheimer's on a biological level, and Alzheimer's is driven by two hallmark features. The first is the build of amyloid beta plaques outside neurons. These sticky protein clumps interfere with cell-to-cell communication and trigger widespread inflammation in the brain. The second hallmark is the development of tau tangles inside neurons, microtubules, but when it becomes hyperphosphorylated, it twists into tangles that disrupt transport within the cell. This eventually leads to neurological death and progressive brain atrophy, especially in the hippocampus, the region of critical memory. These processes explain the severe cognitive decline observed in patients. It's the prevalence of Alzheimer's disease. Alzheimer's is not only a devastating personal disease, but also a growing public health crisis. Over 55 million people worldwide live with the dementia, and accounts for the majority of these cases. In the United States alone, about 5.5 million people are currently affected. The risk of Alzheimer's doubles approximately every 20 years to the age of 65. As longer lifespans expose more individuals to the disease. The graphs here highlight two important trends. First, mortality rates from Alzheimer's have steadily increased over the past 2 decades. And second, projections show cases in the US rising to nearly 13 million by 2050. These trends underscore the urgent need for innovative therapies that can alter the course of the disease. Causes and risk factors. Alzheimer's is driven by both amyloid plaques and tau tangles, and each has different causes and risk factors. Plaques from when mutations in genes like APP, PSEN1, or PSEN2 increase production of toxic amyloid beta peptides. The APOE4 allele also raises risk by reducing the brain's ability to clear amyloid. Tangles, on the other hand, results from hyperphosphorylation, which destabilizes microtubules and causes tau to clump inside neurons. Aging, oxidative stress, and chronic inflammation accelerate this process. Together, these risk factors create a cycle of plaque buildup, tangle formation, and neurological death. Now, what is CRISPR-Cas9? For an overview of CRISPR-Cas9, CRISPR-Cas9 is a revolutionary gene editing tool adapted from a bacterial defense system. It uses a guide RNA to direct the Cas9 enzyme to precise location in DNA, where Cas9 acts like a molecular scissors. Once the DNA is cut, the cell's repair system either disrupt the faulty gene or replace it with the corrected version. This gives researchers a powerful way to turn off harmful the gene or insert protective changes, which makes CRISPR a strong candidate for treating genetic diseases like Alzheimer's. Now, this is the delivery strategy of CRISPR-Cas9. The biggest challenge in using CRISPR is getting the editing tools into the right cells. There are two main categories, viral and non-viral. Viral vectors, especially adeno-associated viruses or AAVs, are widely used because they efficiently deliver CRISPR into neurons, but they can trigger immune reactions and have limited capacity. Non-viral methods include lipid nanoparticles, which package CRISPR components into tiny bubbles that enter cells. And physical approaches like electroporation, these strategies are being refined to improve the safety and precision. Now, the use of CRISPR-Cas9 in curing Alzheimer's. When it comes to Alzheimer's, delivery strategies face an extra the blood-brain barrier. Researchers are designing AAV variants that can cross the barrier and target specific brain regions. Lipid nanoparticles are being tested to carry CRISPR across or to be given intranscranially for a direct access to the brain. Another strategy is receptor-mediated support, which hijacks natural entry points to slip CRISPR into neurons. These approaches are still experimental, but they represent promising steps towards safely editing genes inside the brain. Now, what does this really do, though? CRISPR gives us the ability to go after the disease at its root. For plagues, CRISPR can disrupt the APP-SWE mutation or introduce the protective A673T mutation, lowering amyloid beta production. For tangles, CRISPR can silence tau kinases like GSK3B or directly correct harmful MAPT variants, reducing tau aggregation. For genetic risks, CRISPR can convert ApoE4 into the safer ApoE3 form, which improves amyloid clearance. In short, CRISPR doesn't just manage symptoms, it has the potential to clean up plagues, reduce tangles, and correct the genes that drive Alzheimer's. We'll talk about the challenges of this treatment. Despite its potential, CRISPR-Cas9 faces serious challenges. First, delivery into the brain is difficult because the blood-brain barrier and the complexity of targeting specific neurons. Second, off-target effects remain a concern. CRISPR may sometimes cut unintended DNA sites, causing harmful mutations. Third, the immune system may react against Cas9 protein or viral vectors. Fourth, editing efficiency is not yet high enough to fix enough cells to fully stop the disease progression. Finally, there are ethical concerns, since permanent changes in the brain must be proven safe before use in humans. These challenges must be solved before CRISPR can be a true therapy for Alzheimer's. That is the end of my presentation. I would like to thank my mentor, Hanan, for supporting me throughout the research process. Thank you.
Great job. Thank you so much for sharing more about your research. Again, as a reminder, if anyone has any questions, feel free to add them to that Q&A section that's down in your Zoom. It might be under the More tab. And also, presenters, you're welcome to ask questions of your fellow presenters if you'd like. But I have a question. I was a little curious about if you think that there's any overlap in how gene editing can be used as a treatment for dementia and Alzheimer's, or do you think they're mostly different?
I, I I believe there is an overlap. It's just Alzheimer's has a more of a spread of variety of different type of symptoms. That means there's more like uh, places in the brain that you would have to like specify and deliver the AAVs that I included in the presentation. But yeah, there is definitely an overlap because dementia also falls into the category of Alzheimer's. Just Alzheimer's covers more of a spread into the actual like root itself. So yeah, I do believe there's not much difference and there is an overlap.
Very cool. And then I'm also curious, kind of what do
Mhm.
you imagine being the next step for this project? What would happen next?
I think the next step, I said in the challenges, there are some challenges in for like delivery to the brain, especially the blood-brain barrier, and safety is always important first. I think in the future, like CRISPR-Cas 10, 11, and I think they'll be even more precise in cutting into the DNA and, altering the DNA code. And I think the delivery strategies will be a lot more safer towards the future. I think the idea we have, the foundation, is accurate and is good as of right now. I think in the future, it's just how much safer can we make this treatment method and how much can we use this method in the future.
Perfect. Thank you so much. Yeah, and thank you for sharing.